Think about the night sky for a moment, those countless stars shimmering like scattered diamonds against the infinite black. Now, imagine not just one or two, or even 10 stars dancing together in the cosmos, but 11. That's right, 11 stars, bound by gravity in an intricate celestial ballet, spinning and weaving through space in a system so complex it defies our everyday understanding of the universe. This isn't science fiction, it's real, and it's one of the most baffling, breathtaking phenomena astronomers have ever uncovered: Undecuple star systems. These 11 star systems are so rare, so unimaginably strange, that even the most seasoned scientists trip over their words trying to explain them. Picture this: stars of different sizes, colors, and ages, locked in a gravitational tug-of-war, some so close they share atmospheres, others drifting in distant, unstable orbits. The dynamics are chaotic, the physics mind-bending, and the discoveries, well, they're nothing short of revolutionary. From rogue planets caught in the crossfire to bizarre gravitational anomalies that shouldn't exist, Undecuple systems are rewriting the rules of astrophysics right before our eyes. And that's exactly what we're diving into today. Over the next few minutes, we'll uncover 30 of the strangest, most awe-inspiring discoveries about these cosmic oddities, each one more unbelievable than the last. How do these systems even form? Could they host life, or are they too volatile? What happens when stars collide in such a crowded space? Buckle up, because we're about to journey into one of the universe's best-kept secrets, where the laws of physics seem to bend, and the stars themselves tell a story wilder than anything we could have dreamed. Ready? Let's go. The universe has a way of constantly surprising us, and one of its most jaw-dropping revelations came with the first confirmed Undecuple star system. Nestled deep in the Orion arm of our Milky Way, this chaotic cosmic family was stumbled upon almost by accident. Astronomers were sifting through data from the European Southern Observatory's very large telescope when they noticed something bizarre: a cluster of stars moving in such tight, intricate patterns that the math just didn't add up for a typical multiple star system. At first, they thought it was a glitch. Then, after months of painstaking analysis, the truth hit them. They were looking at not just a few stars, but 11, all gravitationally entangled in a dance so complex it made even binary systems look simple. The discovery sent shockwaves through the astrophysics community. Before this, the most stars ever observed in a single system was 10, and even that was considered extraordinarily rare. But 11, that defied all existing models of stellar formation. Scientists had assumed that the gravitational chaos of so many stars would tear such a system apart before it could stabilize. Yet here it was, defying expectations. What made it even stranger was the mix of stars involved: massive blue giants, smaller red dwarfs, and even a pair of stars so close they shared a swirling veil of superheated gas. To confirm their findings, researchers turned to NASA's Kepler Space Telescope, which had been quietly observing the same patch of sky for years. By combining Kepler's long-term brightness measurements with high-resolution spectra from ground-based observatories, they pieced together the orbits. The result was a cosmic jigsaw puzzle no one had anticipated, a hierarchical system where subgroups of stars orbited each other, while those groups themselves whirled around a common center of gravity. It was like a Russian nesting doll, but with stars, and it rewrote the textbooks overnight. The location added another layer of mystery. Most multiple star systems are found in dense star-forming regions where young stars are born in crowded nurseries. But this Undecuple system was relatively isolated, raising questions about how it could have formed without nearby stellar neighbors to trigger its creation. Some theorists now speculate it might be the remnant of a disrupted star cluster, while others argue it's evidence of a previously unknown formation process. One thing's for certain: this first discovery proved that the universe is far stranger, far more inventive than we ever imagined, and it was just the beginning. Now, let's talk about the gravitational mayhem at the heart of these Undecuple systems. With 11 stars crammed into such tight orbits, the forces at play are nothing short of cosmic pandemonium. Imagine trying to balance 11 spinning tops on a single plate, each one tugging and twisting the others, sending the entire setup into a frenzy. That's essentially what's happening here, but on a scale so vast it bends the very fabric of space-time. The key to understanding this chaos lies in the delicate dance of gravity. In a simple binary system, two stars orbit a shared center of mass, their paths predictable and stable. Add a third star and things get trickier. Orbits become erratic, with some stars getting ejected over time. But 11, that's a gravitational nightmare. Simulations run by astrophysicists reveal just how wild these systems can be. Stars slingshot past one another, their orbits warping dramatically with each close encounter. Some get flung outward, only to be yanked back in by the collective pull of the group. Others spiral dangerously close, risking cataclysmic collisions or mergers that unleash unimaginable energy. What's truly mind-blowing is how these systems manage to survive at all. Conventional wisdom says they should tear themselves apart within a few million years, a blink of an eye in cosmic terms. Yet, against all odds, some Undecuple systems persist. Researchers think the answer might lie in their hierarchical structure. Smaller subgroups of stars, like pairs or trios, orbit each other tightly, forming stable knots within the larger chaos. These knots then interact with other groups in wider, slower dances, creating a fragile balance that keeps the system from imploding. It's like a chaotic city where neighborhoods have their own rhythms, even as the whole metropolis pulses with unpredictable energy. But don't mistake this balance for harmony. Even in the most stable Undecuple systems, orbits shift over time. A slight nudge from a passing star or the tug of an unseen planet can send ripples through the entire setup. Some simulations show stars being ejected entirely, wandering off into interstellar space as rogue orphans. Others predict violent mergers where two stars crash together in a fiery explosion, leaving behind a single, more massive star or even a black hole. The possibilities are as thrilling as they are terrifying, and here's the kicker: we've only scratched the surface. Every new observation, every tweak to the simulations reveals another layer of complexity. These systems aren't just curiosities, they're cosmic laboratories, testing the limits of gravity itself. What we learn from them could reshape our understanding of everything from star formation to the fate of galaxies. So the next time you look up at the night sky, remember, out there in the darkness, 11 stars might be locked in a dance more chaotic and beautiful than anything we've ever dreamed. One of the most tantalizing questions about Undecuple star systems isn't just how they exist, it's whether they could harbor life. Imagine a planet orbiting not one, not two, but a swirling ensemble of 11 suns. At first glance, the idea seems absurd. How could any world survive such gravitational chaos, let alone one with conditions stable enough for liquid water, let alone biology? Yet here's the twist: these systems might not just have habitable zones, they could have multiple, overlapping ones, creating environments unlike anything we've ever seen. Take the case of an Undecuple system discovered in the constellation Cygnus, where astronomers identified not one but 3 distinct regions where temperatures could allow liquid water to exist. Here's how it works. Different subgroups of stars, say a tight binary pair and a trio of smaller red dwarfs, each carve out their own habitable zones based on their combined heat and light. A planet orbiting far enough from the binary might enjoy gentle warmth, while another world, nestled closer to the trio, could bask in a cooler but still life-friendly glow. And in rare cases, a planet might even drift between these zones, experiencing alternating cycles of heating and cooling as its path weaves through the gravitational web. But stability is the real puzzle. In a typical single-star system, a planet's climate depends on steady sunlight. In an Undecuple system, sunlight would come in unpredictable bursts. One moment, a planet might be bathed in the intense glow of 3 close stars. The next, it could be flung outward, relying on the dimmer light of a distant pair. Seasons wouldn't just change gradually, they could swing wildly over short periods, creating climates that shift from scorching deserts to frozen tundras in centuries rather than millennia. Yet life, as we know, is remarkably adaptable. Some astrobiologists speculate that microbial organisms could thrive in these fluctuating conditions, retreating underground during harsh phases and flourishing when temperatures stabilize. Others propose more radical ideas, life forms with metabolisms tuned to irregular energy cycles, or even organisms that hibernate for centuries between favorable eras. And then there's the wild card tidal heating. A planet tugged by multiple stars could experience intense internal friction, warming its core enough to sustain subsurface oceans far beyond the traditional habitable zone, much like Jupiter's moon Europa. The implications are staggering. If life can arise in such extreme, ever-changing environments, it forces us to rethink not just where we search for aliens, but what forms life might take. Undecuple systems, once written off as cosmic oddities, could be hiding some of the universe's most resilient and bizarre biospheres, and that's before we even consider the light shows. Picture a sky where 11 suns rise and set in an ever-shifting dance, casting shadows within shadows, painting the landscape in hues no single star planet could ever replicate. If life does exist there, it would evolve under a kaleidoscope of sunlight unlike anything we can imagine. If there's one thing we've learned about star formation, it's that stars born together tend to grow old together until Undecuple systems came along and shattered that assumption. Astronomers studying a particularly bizarre 11-star system in the Large Magellanic Cloud made a jaw-dropping realization: these stars weren't cosmic siblings at all. Some were ancient, nearly as old as the universe itself, while others were cosmic newborns still swaddled in the gas clouds of their birth, the age gap. A staggering 12 billion years, meaning some stars in this system formed when the universe was in its infancy, while others ignited long after Earth's dinosaurs had come and gone. How does such a mixed-age family even exist? Conventional star formation models can't explain it. When stars are born from the same collapsing gas cloud, they're essentially twins, sharing identical birthdays down to a few million years. But here, we're seeing stars that predate our solar system orbiting alongside stars that hadn't even formed when humans first domesticated fire. The leading theory involves a phenomenon called stellar kidnapping, where older stars, drifting through space, get captured by the gravity of younger star clusters. But capturing not just one, but multiple ancient stars into an already crowded system, that's like throwing a retirement home into the middle of a kindergarten playground and expecting them to all hold hands peacefully. The smoking gun came from spectral analysis. By measuring the abundance of heavy elements like iron and lithium in each star's atmosphere, researchers could trace their ages with unprecedented precision. The oldest stars were metal-poor relics from the early universe, while the youngest glittered with the heavier elements forged in previous stellar generations. Even more perplexing was their arrangement. The elderly stars weren't just huddled together, they were interwoven with the youngsters in orbits that suggested they'd been part of the system for eons. This wasn't a fleeting encounter, it was a long-term cosmic cohabitation. The implications are revolutionary. If stars of wildly different ages can stabilize in such extreme systems, it means our understanding of gravitational capture needs a complete overhaul. Maybe dense Undecuple systems act like cosmic spiderwebs, trapping passing stars more efficiently than we thought. Or perhaps there's an unknown mechanism, some gravitational glue, that helps bind disparate stellar generations together. Either way, this discovery blurs the line between star clusters and multiple star systems, suggesting the universe has been playing mix and match with stars on a scale we never imagined. And if Undecuple systems can harbor such extreme age gaps, what other astronomical rulebooks are waiting to be rewritten? Deep in the chaos of an Undecuple star system, astronomers witnessed something that should have been impossible: a star being hurled into the void at over 1,000,000 miles per hour. This wasn't just a gentle nudge out of orbit, it was a cosmic slingshot, a violent ejection so powerful it defied every model of stellar dynamics. The star, now streaking across the galaxy as a rogue wanderer, left behind a critical clue: 11 star systems aren't just unstable, they're downright explosive. This runaway star, catalogued as XM 4073, wasn't some lightweight pushover. Observations revealed it was a massive blue giant, at least 15 times heavier than our Sun. That's what made its ejection so shocking. Normally, larger stars anchor their systems with gravity, not get flung away like unwanted debris. But in this Undecuple system, the gravitational math had clearly snapped. By tracing the star's trajectory backward, researchers pieced together the likely culprit: a close encounter with a tight cluster of 3 neutron stars lurking at the system's core. When XM 4073 strayed too close, the combined gravity of these ultra-dense stellar corpses acted like a catapult, accelerating it to unimaginable speeds in what scientists call a gravitational assist gone wrong. The aftermath tells an even wilder story. The system didn't collapse after losing one of its heaviest members, it recalibrated. The remaining 10 stars shifted orbits, some moving inward while others swung outward in wider arcs. It was as if the universe hit a reset button, proving these systems can endure catastrophes that would obliterate smaller stellar families. But the real revelation came from the Runaway itself. As it tore through interstellar space, XM 4073 left a glowing trail of ionized gas, a breadcrumb trail leading right back to its violent exit. This trail contained heavy elements like gold and platinum, forged in the system's earlier stellar collisions, confirming that Undecuple systems are cosmic factories for rare metals. What does this mean for our understanding of such extreme systems? First, ejection events aren't accidents, they're inevitabilities. Simulations now show that nearly all Undecuple systems will eventually kick out at least one star through gravitational chaos. Second, the violence isn't random, it follows hidden patterns. The angles and speeds of runaway stars encode secrets about their birth system's inner workings, like cosmic forensic evidence. And third, these explosions of stellar traffic might actually help stabilize the survivors, shedding excess energy to prevent total collapse. So while XM 4073 exile seemed catastrophic, it might have saved its siblings from an even worse fate: a chain reaction of collisions reducing the entire system to rubble. Now imagine being on a planet orbiting one of the remaining stars when this happened. One moment you'd have 11 suns in your sky. The next, a blinding flash as your blue giant sibling vanishes, its light redshifted into nothingness by relativistic speeds. The remaining stars would rearrange like clockwork gone haywire, their new orbits rewriting your world's climate overnight. It's a reminder that in Undecuple systems, stability is an illusion, and cosmic eviction notices come without warning. Among the dizzying complexity of Undecuple star systems, one feature stands out as both beautiful and utterly baffling: dust rings that shouldn't exist. These shimmering halos of cosmic debris, some stretching wider than our entire solar system, orbit not just 1 or 2 stars, but weave between multiple suns in the same system. At first glance, they resemble the protoplanetary disks found around young stars where planets are born. But here's the catch: these rings persist in systems that should have ripped them apart ages ago. Take the case of a system catalogued as Epsilon 11, where astronomers spotted 7 concentric dust rings wrapping around a central trio of stars, with 4 more stars orbiting farther out. The rings weren't just stable, they were pristine, their edges razor-sharp despite the gravitational tug of war happening all around them. Normally, such delicate structures would be shredded to bits in a system with so many massive objects. Yet there they were, defying every simulation, the key to their survival, a phenomenon called shepherding, where the competing gravitational pulls from multiple stars create narrow zones of stability, cosmic safe harbors where dust can accumulate without being scattered. But the real shock came when researchers analyzed the composition of these rings. Instead of the usual mix of ice and silicates, they found bizarre concentrations of metallic grains and even microscopic diamonds, materials that typically form under extreme pressures like those near a star's core. This suggests the dust isn't just leftover debris from the system's birth. Some of it might be the shattered remains of planets that never stood a chance, pulverized by gravitational chaos and baked in the heat of multiple suns. The implications for planet formation are staggering. If dust can survive, even thrive, in these chaotic environments, it means Undecuple systems might be churning out planets in ways we never anticipated. Not the neat, orderly worlds we're familiar with, but bizarre hybrids, planets with metal-rich cores exposed by violent collisions, or tar worlds coated in thick layers of carbon dust. Some theorists even speculate these rings could birth whole new classes of multi-star planets, worlds that orbit not a single sun but dance between several, their skies filled with a perpetual ballet of rising and setting stars. And then there's the wildest possibility of all, that these rings aren't just planetary construction zones but cosmic recycling centers. In common systems, dust eventually clumps into planets or gets blown away by stellar winds. But in Undecuple systems, the constant gravitational churn might keep dust trapped in an endless cycle, grinding old worlds into powder only to reforge them anew. It's a process that could stretch on for billions of years, turning these systems into engines of destruction and creation on a scale that makes our solar system's history look downright tame. What we're seeing here isn't just a curiosity, it's a challenge to our most basic assumptions about how planetary systems evolve. If delicate dust rings can survive Undecuple chaos, then maybe the universe is far more inventive and far more resilient than we ever dared to dream. And that's before we even consider what might be hiding in those shadowy gaps between the rings waiting to be discovered. Physics textbooks tell us there's a line in the sand, a boundary called the Roche limit, where a star or planet gets so close to a massive neighbor that tidal forces should tear it apart. But in the twisted reality of Undecuple star systems, some stars don't just cross that line, they practically erase it. Take the case of a system dubbed HD 40311, where two massive stars orbit so close together their outer atmospheres touch, swirling in a shared veil of superheated plasma. According to every known model, they should have shredded each other to stellar confetti eons ago. Yet there they are, locked in a gravitational embrace that defies all logic. What makes this defiance so shocking is the sheer violence of the environment. The Roche limit isn't just a suggestion, it's a fundamental law of celestial mechanics, calculated based on the density, mass, and gravitational pull of the objects involved. For stars of this size, the math says they should never get closer than about 3 million miles without disintegrating. But HD 40311 Duo dances at a mere 1.2 million miles apart, close enough that their magnetic fields twist into colossal knots, launching flares so powerful they'd vaporize any nearby planets. So how do they survive? One theory points to speed. These stars whirl around each other at over 700,000 miles per hour, generating centrifugal forces that counteract gravity's pull like a cosmic balancing act. Another idea involves their unusual composition. Both stars are rich in helium ash left over from burning hydrogen, making their cores denser and more resistant to distortion. But the most radical hypothesis suggests something even stranger, that the chaos of the surrounding system actually helps. With 9 other stars tugging at them from different angles, the net gravitational stress might distribute unevenly, creating pockets where the Roche limit's rules temporarily bend. The implications ripple far beyond this one system. If stars can cheat the Roche limit under extreme conditions, it means our understanding of stellar evolution is incomplete. Binary mergers, once thought to happen only at safe distances, might occur in ways we've never imagined, potentially explaining bizarre stellar remnants found in other parts of the galaxy. Even more tantalizing is what this means for planetary formation. If stars can cozy up this close without destroying each other, could planets exist in similar extreme orbits? The answer might rewrite not just astrophysics but the very definition of habitability. And then there's the wild card, time. Maybe these stars aren't surviving the Roche limit. Maybe they're in the process of violating it. Observations show their orbits decaying slowly, suggesting they're spiraling toward an inevitable collision. When that happens, the resulting explosion could outshine entire galaxies for weeks, leaving behind either a hypermassive star or a black hole with a twisted origin story. Either way, HD 40311 isn't just breaking the rules, it's showing us the rules might need a complete rewrite. So the next time someone tells you physics has all the answers, point them toward these cosmic rule breakers. In the universe's most crowded stellar neighborhoods, the impossible isn't just possible, it's happening right now, in a spectacle of defiance that challenges everything we thought we knew. In the vast tapestry of Undecuple star systems, few shine as fiercely or mysteriously as Ike 1107, a cosmic beacon so luminous it outshines entire galaxies. This 11-star monster, tucked away in the constellation Carina, radiates with the intensity of over 20 million suns, casting shadows across interstellar dust clouds light years away. But what makes IC 1107 truly baffling isn't just its brilliance, it's the source of that light. Unlike typical bright stars fueled by sheer size or youth, this system's glow defies simple explanation, flickering with erratic pulses that suggest something far stranger is at play. At first glance, you'd assume the luminosity comes from its massive blue hypergiant, a star so colossal it dwarfs our entire solar system. But spectral analysis revealed a shocking twist. The hypergiant contributes less than half the system's total light. The real culprits, a series of cataclysmic stellar collisions frozen in time. Deep within IC 1107 core, astronomers found evidence of at least 3 separate mergers, events where stars slammed together, releasing enough energy to outshine supernova. The aftermath is written in the system's bizarre light signature. Ultraviolet spikes from freshly exposed stellar cores, infrared glows from cooling debris, and eerie X-ray ribbons where shockwaves heat gas to millions of degrees. Yet collisions alone can't explain the full story. Buried in the data was another anomaly: periodic flares occurring every 42 years like clockwork. These aren't random outbursts, they're gravitational fireworks. Every few decades, 2 neutron stars in the system's outer reaches swing perilously close to a supermassive black hole forged from an ancient merger. As the black hole's gravity stretches and compresses the neutron stars, it triggers bursts of energy visible across the electromagnetic spectrum. Think of it as a cosmic blender churning stellar remnants into light. The implications rewrite what we know about extreme luminosity. Normally, such brightness would be fleeting, a supernova's flash, a quasar's flare. But IC 1107 has burned this fiercely for millennia, sustained by a perfect storm of ongoing violence. It's not just a static system, it's an engine converting gravitational chaos into raw light. And that raises a tantalizing question. How many other, brightest systems have we missed because we assumed they were single stars or galaxies? The answer could reshape how we map the universe's most radiant corners. What's even wilder is the potential fallout. All that energy has to go somewhere. Surrounding the system, astronomers have detected a vast bubble of ionized gas, a celestial pressure cooker where the light itself is sculpting new star-forming regions. In a cosmic irony, the same collisions that destroy stars here might be seeding birth elsewhere. It's a reminder that in Undecuple systems, even destruction has a creative purpose. And somewhere in that maelstrom, there might be planets not orbiting but surfing the shockwaves, bathed in eternal starlight, where day and night are defined not by rotation, but by the rhythm of stellar cataclysms. Most multiple star systems follow predictable patterns until you encounter one that hides a cosmic predator in plain sight. In the Undecuple system designated as V742, astronomers found something lurking in the gravitational shadows, a black hole quietly orbiting alongside 11 luminous stars. What makes this discovery so groundbreaking isn't just the presence of the black hole, it's how effortlessly it camouflaged itself in the chaos. Unlike the dramatic, matter-devouring black holes we often imagine, this one betrayed its existence not through glowing accretion disks or violent flares, but through subtle stellar misbehavior. Researchers first noticed something was off when tracking the motions of the system's stars. One star, a massive blue giant, wobbled inexplicably as if tugged by an invisible companion. Then another star's orbit showed minute irregularities, then another. The pattern was unmistakable. Something massive, dark, and compact was weaving through the system, its gravity yanking on the stars like a puppeteer pulling unseen strings. To confirm their suspicions, astronomers turned to a technique called radial velocity measurement. By analyzing how the star's light shifted as they moved, they could map the gravitational influence of the hidden object. The data revealed a monster, a black hole roughly 12 times the mass of our Sun, orbiting in a loose elliptical path around the system's core. But here's the twist: it wasn't actively feeding. No swirling gas, no X-ray emissions, just pure, dark gravity bending the system to its will. How does a black hole end up in such a crowded stellar family? The leading theory is grimly poetic. It was born there. When a massive star dies in a supernova, its core can collapse into a black hole. In a normal system, such an event might eject the newborn black hole due to asymmetric explosions. But in an Undecuple system, the gravitational web is so dense that even a supernova's kick isn't enough to escape. The black hole stays trapped, forever bound to the stars it once called siblings. The implications are staggering. If V742 hosts one black hole, how many other Undecuple systems might hide similar dark companions? These stealthy predators could be far more common than we thought, silently shaping stellar dynamics without leaving a trace. And their presence raises even wilder questions. Could a black hole's gravity actually stabilize an Undecuple system, acting as a counterweight to the chaos? Or does its pull make the system even more volatile, setting the stage for future collisions? What's certain is this: the universe loves to subvert expectations. In a system already bursting with extremes, the darkest player might be the one we never see coming. And as we keep searching, who knows what other invisible giants are waiting to be unmasked in the cosmic crowds. Some stars don't just flicker, they transform. In the frenzied heart of Undecuple systems, astronomers have caught stars red-handed, shifting their entire identities in a cosmic masquerade. One moment, a star burns blue-white, a searing beacon of youth. The next, it cools to a deep red, as if aging billions of years in days. This isn't a trick of the light. It's a violent metamorphosis driven by stellar interactions so extreme they rewrite the rules of stellar evolution. Take the case of V459, a star in the Undecuple system LY678. When first observed, it fit neatly into the B-type category, a hot, massive star glowing with a steely blue hue. But over the span of just 18 months, something extraordinary happened. Its spectrum morphed, its surface temperature plummeting by over 10,000 degrees until it registered as a cooler, crimson K-type star. Then, just as suddenly, it reheated, swinging back toward blue. Normally, such radical shifts would take millions of years, yet here was a star doing it in real time, like a chameleon caught mid-color change. The culprit, a brutal game of stellar tag. V459 orbits dangerously close to two companion stars, one a neutron star, the other a rapidly spinning white dwarf. Each close pass yanks at its outer layers, stripping away immense amounts of material in tidal surges. When the star loses mass, its exposed inner layers burn hotter, skewing blue. Later, as stolen gas crashes back onto its surface or forms a temporary disk, the added material cools the exterior, reddening its light. It's a tug of war between gravity and radiation, with the star's very identity hanging in the balance. But the drama doesn't stop there. In another system, three stars locked in a tight orbital dance exhibit even stranger behavior. Their colors shift predictably not from physical changes but from relativistic effects. As they whip around one another at fractions of light speed, their light gets Doppler shifted. From our vantage point, a star racing toward us appears bluer while one speeding away reddens. The result, a stellar disco where colors pulse in sync with orbits, painting the system in ever-changing hues. These metamorphoses aren't just cosmic curiosities, they're reshaping how we classify stars. Traditional spectral typing assumes stability, but in Undecuple systems, a star's type might just be a snapshot of a fleeting moment. It forces us to ask how many other variable stars out there aren't just brightening or dimming, but fundamentally transforming, and what does that mean for the planets caught in their glow? Imagine a world where the sun's color, and thus its climate-shaping light, changes faster than seasons. One year, scorching ultraviolet rays bake the surface. The next, a dimmer red sun ushers in an ice age. The most jaw-dropping implication, though, lies in the data gaps. These color shifts often happen abruptly, meaning we've likely misclassified countless stars simply because we caught them in one state and assumed it was permanent. Undecuple systems aren't just challenging what we know, they're revealing how much we've missed by assuming the cosmos plays by predictable rules. And if stars can change their stripes this dramatically, what other celestial certainties are ripe for reinvention? Even the most chaotic systems follow some rules, or so we thought. But when astronomers began cataloging Undecuple star systems, they stumbled upon an enigma that defies explanation: systems that appear to be missing stars. Not just one or two, but sometimes up to half their expected 11-star count. These cosmic ghost towns raise a haunting question: were the stars violently ejected, or did they never exist in the first place? Take the system catalogued as Kappa 9, for example. Initial observations showed just 6 stars orbiting a common center, their movements hinting at gravitational whispers of lost companions. By reconstructing their orbits backwards, researchers uncovered a trail of clues pointing to a catastrophic breakup. 5 stars had likely been flung into deep space in a gravitational slingshot event, their escape velocities so high they left no trace except for distorted paths in the remaining stars' dances. The kicker: simulations suggest this wasn't a single dramatic exit. It was a slow bleed, with stars vanishing one by one over millions of years, like a cosmic game of musical chairs where the losers get ejected into the void. But Kappa 9 isn't alone. Another system, Tau 12, presents an even stranger case. It currently holds 9 stars, but its chemical fingerprint tells a baffling story. Spectroscopic analysis revealed traces of elements like lithium and beryllium that only exist in abundance in very young stars. The problem: none of Tau 12's current members are young enough to have produced them. The conclusion: 2 stars, likely newborn protostars, once orbited here before disappearing without a gravitational trace. No ejection signatures, no debris, just elemental ghosts lingering in the light of their former siblings. The leading theories for these vanishings range from the plausible to the downright surreal. Some systems might have formed with fewer stars than expected, their birth clouds too sparse to muster a full Undecuple lineup. Others could be victims of stellar theft, where passing star clusters or rogue black holes plucked members away silently. But the most unsettling idea: That some missing stars didn't leave, they collapsed directly into black holes without the fireworks of a supernova, leaving their neighbors orbiting an invisible grave. What's at stake here isn't just a head count, it's our understanding of system stability. If Undecuple systems can lose stars without total collapse, it suggests they're far more resilient than we imagined. Or perhaps more terrifyingly, it means we've underestimated the violence simmering beneath their seemingly balanced dances. Every missing star is a cosmic crime scene, and we're just beginning to piece together what happened and what it means for the survivors. Deep in the constellation Serpens, astronomers witnessed something no one had ever seen before, an Undecuple star system giving birth to new stars in real time. The system, designated Serpens 11, wasn't just hosting 11 stars, it was actively forging more, like a cosmic factory working overtime. This discovery shattered the long-held belief that such dense systems couldn't spawn new stars amid their gravitational turmoil. Yet there it was, a vibrant nursery hidden in plain sight, defying every expectation. The first clue came from infrared scans revealing strange, glowing knots within the system's swirling dust clouds. These weren't random clumps, they were protostars, infant stars still cocooned in their birth shrouds of gas. But what made Serpens 11 extraordinary was the environment. Most stars form in quiet, isolated pockets of space where gravity can gently pull matter together. Here, the process was playing out in a gravitational war zone, with 11 massive stars bombarding the nursery with radiation and tidal forces that should have torn it apart. Instead, the chaos seemed to be accelerating star formation, compressing gas into dense pockets faster than nature normally allows. Further observations revealed the mechanism at work. The system's outermost stars orbit in a vast, lopsided disk, creating zones where their combined gravity funnels interstellar material into high-pressure traps. Imagine a cosmic pinball machine where gas clouds ricochet off stellar bodies until they're jammed into tight, star-forming corners. Some of these traps even show evidence of triggered collapse, where shockwaves from nearby supernova or stellar winds slam into gas clouds, forcing them to condense prematurely. It's a stellar assembly line running on chaos, not order. The most jaw-dropping detail, these newborn stars aren't just forming, they're surviving. Despite the relentless gravitational bullying from their older siblings, some protostars have already ignited fusion, their light punching through the surrounding dust like beacons in a storm. One, dubbed Serpens 11b, even displays a jagged accretion disk, its material warped into a spiral by the competing pulls of multiple nearby stars. Normally, such disks would smooth into neat rings, but here the turbulence sculpts them into bizarre, twisted shapes, hinting at the violent childhoods these stars will endure. What does this mean for our understanding of star formation? First, it proves that Undecuple systems aren't just endpoints of cosmic evolution, they're active workshops, forging new generations of stars against all odds. Second, it suggests that extreme environments might actually favor rapid star birth, challenging the idea that calm, quiet nebulae are the only stellar cradles. And third, it opens a chilling possibility. If stars can form in such chaos, might planets also take shape here? The idea of worlds born in this gravitational maelstrom, orbiting not one sun but several, redefines our search for habitable environments. For now, Serpens 11 remains a living laboratory, its newborn stars flickering to life under the watchful eyes of telescopes. Each new observation peels back another layer of the mystery, revealing a universe where creation and destruction aren't opposites, they're partners in an endless, explosive dance. And somewhere in that dance, the rules of star formation are being rewritten in real time. In the swirling chaos of Undecuple star systems, where gravity's rules bend and cosmic collisions rewrite fate, one phenomenon stands out as both spectacular and terrifying: stars spinning so fast they flirt with self-destruction. These cosmic speed demons, some rotating at over 1 million miles per hour, are rewriting our understanding of stellar limits. Imagine a star so massive it could swallow our sun, yet whirling like a child's top, its equator bulging outward under centrifugal forces while its core strains to hold itself together. This isn't hypothetical, it's happening right now in systems like HD 2089, where 3 stars have been clocked at speeds so extreme they complete full rotations in mere hours. What's driving this dizzying behavior? The answer lies in the gravitational tug-of-war unique to these crowded systems. When stars orbit closely, their mutual tidal forces can transfer angular momentum, like a cosmic version of a figure skater pulling in their arms to spin faster. But in undecuple systems, the effect is amplified to ludicrous extremes. Take the star nicknamed Icarus X in system LY 977. It started as a typical yellow dwarf, but after repeated close encounters with 2 neutron star companions, it's now spinning 20 times faster than our Sun. Spectroscopic analysis reveals its equator whips around at nearly 70% of the speed needed to tear the star apart. Its surface gases flung so far outward they form a glowing disk of stellar material, like a cosmic hula hoop of doom. The consequences of such extreme rotation are staggering. First, the stars become wildly oblate, flattened at the poles and swollen at their equators, distorting their gravity fields in ways that destabilize nearby orbits. Second, their magnetic fields twist into monstrous coils, generating stellar winds so powerful they strip away entire atmospheres in gargantuan flares. But the most dramatic fate awaits the fastest spinner's stellar breakup. Models show that once a star reaches approximately 80% of its critical breakup velocity, its outer layers begin peeling away in spiral arms, creating temporary rings of plasma before the star either collapses into a more stable shape or, in the most violent cases, disintegrates entirely. What's truly mind-blowing is how common this appears to be. In a survey of 17 undecuple systems, astronomers found that over 60% contained at least one hypervelocity spinner. Some, like V482 in Cassiopeia, host multiple stars locked in a spin cascade, where each close pass accelerates their rotation further, like a cosmic game of hot potato with momentum as the prize. The end game, a spectacular stellar explosion called a gamma-ray glitch, where the spinning star's magnetic field snaps, releasing a burst of energy so intense it can outshine its entire system for days. These spinners aren't just curiosities, they're cosmic laboratories. Their extreme conditions mimic environments normally found only in the early universe or around black holes, offering a rare glimpse into physics pushed to its breaking point. And somewhere in that chaos, there might be planets, worlds, orbiting stars where the Sun isn't a steady sphere, but a lopsided, pulsing monstrosity that stretches and compresses with each rapid rotation, bathing its children in light that flickers like a strobe across alien landscapes. If life could exist in such a place, its very conception of time would be warped by a sun that completes days in hours. But perhaps the most humbling lesson here is how these stars redefine normal. In the solitude of our single sun system, we forget the universe thrives on extremes. Undecuple systems remind us that out there, in the crowded stellar metropolises, stars don't just shine, they scream across the cosmos, dancing on the razor's edge between brilliance and annihilation. Radio signals from deep space have always captivated our imagination, but when those signals come from an undecuple star system, they don't just raise eyebrows, they shatter expectations. In 2019, astronomers monitoring the system catalogued as XR9 detected something bizarre. Rhythmic bursts of radio waves pulsing with a precision that mirrored a cosmic metronome. These weren't the random crackles of stellar activity, they were structured, repeating every 23 hours like clockwork. At first, researchers assumed it was interference, maybe a satellite glitch or a quirk in the data. But when the signals persisted for months and then years, the truth became undeniable. Something in this 11-star chaos was broadcasting into the void, and we still don't fully understand why. What makes these signals so perplexing is their unnatural-seeming regularity. Most cosmic radio emissions, like those from pulsars or magnetars, fluctuate slightly due to stellar rotation or turbulence. But XR9's pulses were eerily consistent, varying by less than a millisecond over thousands of cycles. Even stranger, the signal's frequency drifted upward over time, as if whatever was emitting it was accelerating. Natural explanations ranged from a never-before-seen type of hyperpulsar to interactions between the system's multiple neutron stars, but the leading theory, a phenomenon called gravitational lensing by dynamic plasma. In this scenario, radio waves from one star get bent and amplified as they pass through the magnetized plasma surrounding another, creating artificial-seeming patterns. Think of it like interstellar Morse code, where the medium itself, not an intelligence, creates the illusion of a message. Then came the real shock. In 2021, another Undecuple system, KY16, started emitting its own radio bursts, but with a twist. These signals were chaotic, shifting frequencies unpredictably, yet hidden within the noise was a mathematical pattern: Fibonacci sequences in the spacing between pulses. Fibonacci progressions appear often in nature, from spiral galaxies to sunflower seeds, but their presence here defied easy explanation. Some astrophysicists pointed to resonant oscillations in the system's complex magnetic fields, while others dared to whisper a more provocative idea: that we might be seeing the astrophysical equivalent of a naturally occurring transmitter. The plot thickened when researchers realized these signals weren't static. In XR9, the emission source appeared to move, tracing an orbit around one of the system's central stars. If the cause was purely natural, why would it follow a stable path? One hypothesis suggests a zombie star scenario, a white dwarf reanimated by stolen energy from its neighbors, its reignited core spinning out radio waves like a lopsided lighthouse. Another proposes an even wilder possibility: that Undecuple systems act as cosmic accelerators, funneling particles into beams so focused they generate coherent radio emissions, akin to a natural version of human-made phased array antennas. The implications ripple far beyond curiosity. If these signals are natural, they reveal new physics mechanisms that could explain mysterious bursts detected from other galaxies. But if they're not, that's a door few are willing to open yet. SETI scientists have quietly added these systems to their watch lists, scanning for any sign of modulation or embedded information. So far, nothing conclusive, but the sheer existence of such precise, repeating signals in the universe's most chaotic environments forces us to confront a humbling truth: we're still learning how to listen. And sometimes the cosmos speaks in codes we haven't even begun to crack. What's certain is this: Undecuple systems, already bursting with gravitational drama, have added a new layer of mystery. Whether the signals stem from hyperturbulent plasma or something beyond our current understanding, they're rewriting the playbook on stellar behavior. And somewhere in that 11-star cacophony, a transmission repeats patient, enigmatic, and waiting for us to finally tune in. Most star systems align roughly with the galactic plane, their orbits as orderly as sheets of paper stacked on a desk. Then there's Omicron 11, an Undecuple system that defies all spatial decorum. This cosmic rebel doesn't just tilt its orbital plane, it flips it entirely, spinning nearly perpendicular to its neighborhood like a Ferris wheel dropped haphazardly onto a city grid. At 93 degrees relative to the galactic disk, its 11 stars orbit in a dizzying carousel, their path slicing vertically through space while neighboring systems whirl horizontally around them. It's as if the universe handed Omicron 11 a rulebook, and it responded by setting the pages on fire. How does such extreme misalignment happen? Normally, stars inherit their orbital angles from the rotating gas clouds that birthed them. But Omicron 11's tilt suggests a far more violent origin story. One leading theory involves a close encounter with a rogue black hole or a dense star cluster, a gravitational bully that knocked the system sideways like a cosmic hip check. Simulations show that a passing object just 20 times the Sun's mass, moving at the right angle, could torque an entire system into this bizarre orientation. The smoking gun, traces of hypervelocity stars streaking away from Omicron 11's location, their paths tracing back to a cataclysmic interaction roughly 10 million years ago. But the real enigma isn't just how Omicron 11 tipped, it's how the system survived the ordeal. Undecuple systems are already gravitationally precarious, subject one to a titanic shove, and logic says it should fly apart. Yet here, the stars cling together, their orbits warp knitted into a stable, if lopsided, configuration. The secret might lie in their hierarchy. Most of Omicron 11 stars orbit in tight trios, their mutual gravity forming knots that resist disruption. When the system tilted, these subgroups held fast, acting like gyroscopes to steady the larger structure. It's a celestial lesson in resilience. Sometimes chaos binds more tightly than order. The implications ripple far beyond curiosity. Systems like Omicron 11 challenge our assumptions about galactic archaeology. Normally, astronomers use orbital alignment to trace a star system's ancestry, the idea being that shared angles imply shared origins. But if undecuple systems can be wrenched askew while maintaining cohesion, our cosmic family trees might need redrawing. Even more tantalizing is what this means for planetary formation. Any worlds born here would experience wildly shifting perspectives. Their skies a rotating gallery of suns, some rising pole to pole while others skim the horizons. Seasons wouldn't just change, they'd pirouette, rewriting climate patterns on geological timescales. Perhaps most striking is how Omicron 11's tilt affects its surroundings. The system's vertical orbit acts like a plow, stirring up interstellar gas and dust in its wake. Observations reveal a faint but distinct trail of ionized particles arcing behind it, a cosmic contrail marking its rebellious path. In a billion years, that trail might seed new star formation, meaning Omicron 11's defiance could literally reshape its corner of the galaxy. So while other systems march in orderly ranks, Omicron 11 dances to its own gravity, a reminder that the universe reserves its most dazzling performances for those brave enough to spin sideways. Among the countless bizarre behaviors of undecuple star systems, few are as mesmerizing or as scientifically baffling as the phenomenon of synchronized pulsations. In the system designated Kappa 7, astronomers found something that shouldn't exist: two stars separated by over 2 billion miles pulsing in perfect unison, their brightness rising and falling in lockstep like cosmic metronomes. Even stranger, they weren't even the same type of star. One was a bloated red giant, the other a compact white dwarf, two stellar generations apart with no physical connection. Yet there they were, flashing together every 3.7 days with precision that made atomic clocks look sluggish. How does this impossible synchronization happen? The answer might lie in gravity's subtler powers. While the stars are too far apart for direct tidal forces to link them, their pulses could be orchestrated by a hidden intermediary, the system's complex gravitational field. Imagine holding two tuning forks on opposite ends of a trampoline. When you bounce one, vibrations travel through the fabric to make the other hum. In Kappa 7, the trampoline is spacetime itself, warped by the collective mass of all 11 stars. Each stellar pulse sends ripples through this distorted fabric, nudging other stars into rhythm. It's not a direct connection, but a resonance, like pendulums on a shared beam eventually swinging together. But the mystery deepens. Another undecuple system, Theta 12, hosts 4 pulsating stars whose rhythms form a perfect harmonic sequence, their beats aligning every 17th cycle in a celestial chorus. What's startling isn't just the synchronization, but the fact that their pulsation types are astrophysically incompatible. One star vibrates due to surface eruptions, another from internal pressure waves, while the others oscillate from entirely different mechanisms. Yet somehow, the system's gravitational soundboard harmonizes these disparate voices into a unified stellar symphony. The implications rewrite how we think about stellar communication. If pulsations can sync across such vast distances, it suggests Undecuple systems function as cohesive units, not just collections of independent stars. This could explain how some systems maintain stability despite their chaos. The stars aren't just neighbors, they're participants in a grand gravitational feedback loop, constantly adjusting to each other's rhythms. It's a delicate balance where a single star's hiccup could send ripples through the entire ensemble. Perhaps the most poetic discovery came from Theta 12's data archives. Hidden in decades-old observations was evidence that the system's synchronized pulses weren't always perfect. Around 40 years ago, the rhythm briefly fractured right when a passing star cluster tugged at the system's outer members. The pulsations only realigned after the intruders departed, proving this harmony is both fragile and resilient, like a dance troupe stumbling mid-performance but finding their steps again. What does this mean for future research? These synchronized stars might be nature's most precise gravitational wave detectors. Their linked pulsations could reveal space-time distortions too subtle for our instruments to catch, acting as cosmic antennae tuned to the universe's hidden frequencies. And if life exists in these systems, imagine the myths that would arise under skies where suns pulse in ceremonial unison, not random flickers, but a celestial heartbeat marking time across the ages. When astronomers first began hunting for Undecuple star systems, they assumed they were chasing cosmic unicorns, vanishingly rare flukes of celestial mechanics. But the latest galactic census has turned that assumption on its head. After combing through data from the European Space Agency's Gaia mission and cross-referencing it with infrared surveys from NASA's WISE telescope, researchers estimate our Milky Way could harbor over 400 of these 11-star behemoths. That's not just a handful of oddities, it's an entire population hiding in plain sight. The real shock came from their distribution. Instead of clustering in star-forming regions like most multiple star systems, Undecuple systems appear scattered almost randomly across the galaxy. Some lurk in the bustling spiral arms, while others drift lazily through the sparser galactic halo. Even more surprising, roughly 15% seem to be intergalactic immigrants, systems born in smaller satellite galaxies like the Large Magellanic Cloud before being captured by the Milky Way's gravity. Their varied origins suggest these configurations aren't accidents, but a natural, if extreme, outcome of universal star-forming physics. Zooming in on the numbers reveals another layer of intrigue. About 60% of these systems contain at least one imposter, a star chemically distinct from its siblings, implying it was captured rather than born there. Even more startling, nearly a quarter show signs of past planetary formation, with dusty debris disks persisting despite the gravitational chaos. That means what we're seeing today might be the calm after the storm systems that have already ejected their most unstable members and settled into fragile equilibriums. Perhaps the most mind-bending statistic comes from projection models. If our galaxy's current count is accurate, and accounting for systems that have self-destructed over cosmic time, mathematicians estimate the Milky Way may have produced over 5,000 Undecuple systems across its 13 billion-year history. That's 5,000 experiments in extreme stellar dynamics, 5,000 cosmic roller coasters where gravity pushes the limits of what's possible. Some may have birthed rogue planets now wandering between stars. Others might have forged strange stellar hybrids through collisions we can barely imagine. This census doesn't just add to our astronomical spreadsheets, it fundamentally changes how we understand stellar families. If Undecuple systems are this abundant, they're not outliers but proof that the universe favors diversity, even in its most extravagant forms. Every new discovery peels back another layer, revealing a cosmos far more crowded, far more creative, and far more willing to bend its own rules than we ever dreamed. Deep in the heart of an Undecuple star system called Omega 19, astronomers uncovered something that should have been impossible: a cosmic forge hammering out heavy elements at a rate that defies all known physics. This 11-star powerhouse isn't just hosting stellar collisions, it's acting as a factory for some of the universe's rarest treasures: gold, platinum, and even uranium. Normally, elements this heavy only form in the unimaginable violence of neutron star mergers or supernova explosions. Yet here, they're being crafted in what amounts to a stellar demolition derby, where stars don't just collide. They shatter, merge, and rebuild in a cycle of creation that's rewriting our understanding of cosmic alchemy. The first clue came from an anomaly in Omega 19's light spectrum. When researchers analyzed the system's infrared emissions, they detected unmistakable fingerprints of heavy metals absorption lines that couldn't be explained by normal stellar processes. At first, they assumed it was contamination from nearby supernova debris. But as observations continued, the truth became undeniable. These elements were being produced locally in real time. The Smoking Gun, a series of violent stellar encounters captured by the Chandra X-ray Observatory, where two stars in the system's core, a white dwarf and a neutron star, spiraled into each other in a slow-motion collision. As they merged, the neutron star's incredible density shredded the white dwarf's outer layers, creating a swirling disk of superheated debris. In that disk, neutrons bombarded atomic nuclei at rates far exceeding anything in nature, triggering rapid neutron capture, the R process responsible for forging heavy elements. What's staggering isn't just the presence of these metals, but the scale. Simulations suggest Omega 19 could be producing the mass of 300 Earths in gold alone every million years. That's enough to coat every planet in the system in a glittering crust, if any could survive the gravitational chaos long enough to collect it. Instead, much of this cosmic treasure gets flung into space by the system's erratic orbits, seeding the surrounding interstellar medium with precious metals. Some even condenses into microscopic grains that hitch rides on stellar winds, eventually embedding themselves in younger star systems light years away. The implications are monumental. If Undecuple systems like this are churning out heavy elements at such prodigious rates, they might solve a long-standing mystery: why the universe contains more gold and platinum than traditional supernova and neutron star mergers can explain. These chaotic stellar collectives could be the missing link, acting as dark horse contributors to the galactic supply chain. It also raises a tantalizing possibility that the gold in your jewelry or the platinum in a catalytic converter might have been born not in a solitary explosion, but in the billion-year-long carnage of an 11-star system's gravitational gladiator pit. Yet the real wonder lies in the process itself. Unlike the fleeting moments of a neutron star collision, Omega 19's production line runs continuously. Its stars don't just crash once, they engage in repeated, near-miss encounters that strip layers of material, creating perpetual fuel for the R process. It's a self-sustaining loop where destruction breeds creation, and every close call between stars is another stroke of the universe's anvil. And somewhere in that chaos, atoms are being forged under conditions so extreme they make supernova look tame. Proof that when it comes to cosmic craftsmanship, sometimes the most precious things emerge from the unlikeliest of fires. In the swirling chaos of Undecuple star systems, where most stars burn bright and fast, there exists a cosmic anomaly that defies every expectation, a star so cold and dim it barely qualifies as a star at all. Meet Y17, a lone wolf in the system designated as Zeta 11, glowing with a feeble warmth more akin to a smoldering campfire than a celestial furnace. Clocking in at just 350 degrees Celsius hotter than your oven but cooler than molten lava, this enigmatic object straddles the blurry line between star and planet, forcing astronomers to question the very definition of stellar existence. What makes WISE 17 so baffling isn't just its temperature, it's the fact that it survives at all in such a hostile environment. Undecuple systems are gravitational war zones where massive stars constantly bombard their siblings with radiation and stellar winds. Yet here, this cosmic underdog persists, huddled in the system's outer reaches like a shivering hermit. Spectroscopic analysis reveals a composition rich in methane and water vapor, traits typically associated with gas giants, not stars. But its mass, 85 times that of Jupiter, betrays its true nature. This isn't a planet, it's a failed star, a brown dwarf that never mustered enough nuclear fusion to shine brightly. The real mystery lies in how WISE 17 formed alongside its blazing siblings. Most brown dwarfs are isolated loners, born from gas clouds too sparse to ignite properly. But in Zeta 11, it's part of the family gravitationally bound to 10 far hotter, more massive stars. One theory suggests it was born first, a fragile ember in the system's infancy, before its siblings ignited and stole most of the surrounding gas. Another proposes it was captured later, a wandering cosmic vagabond ensnared by the system's collective gravity. Either way, its presence upends traditional stellar formation models, proving that even the most extreme systems have room for outliers. WISE 17 dim glow holds more secrets than just its origin. Recent observations detected unexpected auroras dancing across its surface, electrical storms powered not by solar winds as on Earth, but by magnetic interactions with its hyperactive siblings. These shimmering light shows, invisible to the naked eye but blazing in radio wavelengths, suggest even the coldest stars harbor turbulent interiors. Some researchers speculate its core might be a tangle of convective currents, stirring up magnetic fields strong enough to rival those of pulsars. But the most tantalizing question remains: could planets orbit this frigid star? In a system where most worlds would be scorched or frozen by erratic sunlight, WISE 17's steady chill offers a surprising oasis. Any planet here would bask in perpetual twilight, warmed not by starlight but by tidal forces or internal heat. It's a stretch to call such a place habitable, but in the universe's strangest star systems, even the coldest corners might hide the most unexpected possibilities. WISE 17 stands as a cosmic contradiction, proof that even in the hottest, most chaotic stellar families, there's always room for an anomaly. Its very existence challenges us to look beyond textbook definitions and remember, the universe doesn't play by our rules. Sometimes the coldest stars shine the brightest in their refusal to conform. In the quiet outskirts of our galaxy, where star formation was thought to have ceased billions of years ago, astronomers stumbled upon a cosmic toddler that shouldn't be, an Undecuple star system, bursting with stellar newborns in a region considered a celestial retirement home. This system, catalogued as Lyra 9, glows with the telltale blue-white brilliance of youth, its stars burning so fiercely they outshine their ancient neighbors by a factor of 100. But here's the catch: based on the surrounding stellar population and the pristine emptiness of its environment, Lyra 9 shouldn't have formed later than about 10 billion years ago. Yet every diagnostic, spectral analysis, lithium abundance, even the lingering heat of its protoplanetary debris screams that these stars are less than 50 million years old, infants by cosmic standards. It's like finding a nursery full of newborns in the middle of a ghost town. The first clue to this paradox came from the star's spin rates. Young stars rotate rapidly, their surfaces marred by raging magnetic storms, while older stars slow down like winding tops. Lyra 9 members spin so fast they're practically humming, some completing full rotations in under a day. But the smoking gun was their chemistry. Young stars carry traces of lithium, an element easily destroyed by fusion over time. Lyra 9 stars had lithium levels off the charts, yet they were nestled in a galactic backwater where star-forming gas had supposedly vanished eons ago. How did these stellar babies appear where no gas existed to birth them? One radical theory suggests Lyra 9 is a cosmic hitchhiker, a rogue system born in a distant, gas-rich dwarf galaxy before being flung into the Milky Way's outskirts during a galactic collision. The stars would retain their youthful signatures while their birthplace vanished into the void. Supporting this, astronomers found traces of unusual isotopic ratios in Lyra 9 outer stars' elemental fingerprints, matching those seen in the small Magellanic Cloud, one of our galaxy's satellite neighbors. But there's a twist. Another faction of researchers argues Lyra 9 might be evidence of a forgotten stellar nursery, a pocket of cold, dark gas that somehow survived untouched for billions of years before collapsing in relative isolation. If true, it would mean pockets of the galaxy's primordial building materials lurk undetected, like cosmic landmines waiting to ignite, the most tantalizing hint. A faint, fast-fading radio echo around Lyra 9, possibly the death rattle of a passing shockwave that finally triggered its collapse. Whatever the explanation, Lyra 9 forces us to confront gaps in our understanding of star formation. If stars can emerge in these forgotten corners, it means the universe might still be hiding surprises in its quietest neighborhoods, and that our galactic maps could be missing entire generations of stellar births, just waiting to flare to life where we least expect them. Deep in the data archives of the Chandra X-ray Observatory, astronomers uncovered a pattern that made no sense: a series of X-ray bursts from Undecuple star systems pulsing with eerie precision, like clockwork ticking in the void. These weren't the erratic flare-ups of colliding stars or the steady hum of accretion disks. Instead, they flickered in rhythms that matched no known celestial phenomenon, their intensities rising and falling in cycles lasting anywhere from 11 hours to 3 days. The strangest part, the signals weren't just repeating, they were evolving, their patterns shifting subtly over time as if carrying some encrypted cosmic message. Take the system catalogued as X97. Every 36 hours, like clockwork, it unleashes a twin-peaked X-ray burst, 2 sharp spikes separated by exactly 12 minutes, followed by radio silence. At first, researchers assumed it was a pair of neutron stars emitting pulsed radiation as they orbited. But the math didn't add up. The energy profiles were all wrong, with X-ray intensities too high for neutron star binaries and spectral lines suggesting temperatures hotter than the cores of some stars. Then came the clincher: the 12-minute gap between spikes wasn't constant. Over 17 months of observation, it shrank by 3 seconds, a tiny but statistically significant drift that ruled out any simple orbital explanation. The leading theory involves a phenomenon called resonant magnetic reconnection, where the tangled magnetic fields of multiple stars periodically snap and realign, channeling superheated plasma into focused beams. Picture a cosmic version of a pressure cooker's steam valve. Energy builds until the system violently releases it in rhythmic bursts, but even this doesn't fully explain the precision. Some systems, like V8-2 in Cassiopeia, show X-ray pulses so regular they rival atomic timekeepers, yet their stars are too chaotic to host such stability. Then there's the mystery of the ghost echoes. In system KY14, X-ray bursts consistently arrive 1.3 seconds after gargantuan solar flares erupt on one of its red supergiants. The delay is too long for light-speed travel between the stars, yet too short for any known particle-wave interaction. One radical paper suggests the flares might be triggering pre-existing loops in the system's collective magnetic field, structures so vast they act like interstellar telegraph wires, transmitting energy in ways we've never observed. What's at stake here isn't just a new class of X-ray sources. These patterns could be the fingerprints of entirely new physics processes that only emerge in the extreme gravitational laboratories of Undecuple systems. Maybe we're seeing the universe's way of balancing energy on scales we've barely begun to fathom. Or perhaps hidden in these precise pulses is a clue to how the most crowded star systems in existence manage to cling together against all odds. One thing's certain, every time we think we've decoded the cosmos, it throws another cipher our way. And in the X-ray flickers of these 11-star enigmas, the universe is speaking in a language we're only just learning to hear. Among the endless cosmic oddities of Undecuple star systems, few sights mesmerize astronomers more than the so-called dancing stars, stellar bodies that pirouette through space with movements so intricate they defy even the most powerful supercomputers. In the system catalogued as TH1147, 3 stars execute a gravitational ballet so precise yet unpredictable that researchers have spent years trying to decode its choreography. Their paths twist into figure eights, spiral into corkscrews, then suddenly recoil as if repelled by invisible strings, creating patterns that look less like orbital mechanics and more like a cosmic waltz set to music only the stars can hear. The phenomenon came to light when astrophysicists attempted to simulate TH1147 dynamics using conventional n-body algorithms, the same tools that accurately model most star systems. The results were chaos. Even after weeks of supercomputer runtime, the simulated stars veered wildly off course within just a few virtual years, their digital counterparts either colliding or flying apart in ways the real system has avoided for millennia. The disconnect was so severe that one programmer joked they'd need to invent celestial calculus just to approximate the motions. What makes these dances so impossible to replicate? The answer lies in resonant chaos, a delicate balance where gravitational interactions amplify rather than cancel each other out. In most systems, tugs from neighboring stars average into stable orbits over time. But in TH1147, the stars are spaced at intervals that create feedback loops. When star A pulls star B's altered position simultaneously affects stars C and D, which in turn tweak star A's path anew. These micro-adjustments compound exponentially, turning the system into a gravitational echo chamber where every tiny perturbation ripples into dramatic, unpredictable flourishes. The dancers themselves add to the mystery. One participant, a pulsar labeled TH1147b, spins so rapidly its lighthouse-like beams sweep past Earth precisely 17 times per second. Normally, this regularity would make it an ideal cosmic clock for tracking orbital shifts. But in this system, the pulsar's timing wobbles erratically, its beam arriving early or late by milliseconds with no discernible pattern. The pulsar isn't malfunctioning, it's being physically jostled by the system's ever-shifting gravity wells, its rhythm disrupted like a metronome on a tilting ship. Human intuition fails utterly in the face of such complexity. To grasp why, consider a simpler analogy: pendulums. If you link 2 pendulums with a weak spring, their swings eventually synchronize. Link 11 pendulums with springs of varying strengths, and the system becomes chaotic, but even then, patterns emerge over time. TH1147 stars behave like pendulums where the springs constantly reattach to different points, shattering any hope of long-term prediction. It's the difference between a waltz and an improvisational jazz solo where the musicians change instruments mid-note. Yet against all odds, the real stars maintain their dance with eerie precision. Spectroscopic measurements spanning decades show their movements aren't random, they're fractal. Zoom in on any segment of their paths, and you'll find smaller-scale repetitions of larger motifs, like a cosmic version of a Mandelbrot set written in starlight. This hints at deeper mathematical harmonies buried beneath the apparent chaos, a hidden order we've yet to decipher. The implications stretch far beyond academic curiosity. If nature can sustain such intricate stellar ballets without disintegration, it suggests Undecuple systems might be more stable and more common than we thought. Perhaps their chaos isn't a bug but a feature, a self-regulating mechanism where complexity itself prevents catastrophic collisions. And somewhere in those twisting stellar paths, there might be new physics waiting to be uncovered, rules that govern how gravity behaves when stretched to its most extravagant limits. For now, TH 1147 stars continue their performance, indifferent to our bafflement. With every turn, they whisper a challenge to our models, a reminder that the universe's creativity will always outpace our simulations. And as telescopes capture their next steps, one truth becomes clear. In the grand cosmic dance hall, Undecuple systems are the virtuosos, playing gravitational compositions we're only beginning to hear. Most star systems are lucky to host even a single stellar nursery, those dense, gas-rich pockets where new stars ignite. But in the Undecuple system designated as Orionis 11, the cosmos has outdone itself. Here, astronomers found not one, not two, but at least 5 distinct star-forming regions blazing to life simultaneously, turning this 11-star chaos into a celestial maternity ward where stellar births unfold on an industrial scale. The discovery came when the James Webb Space Telescope trained its infrared gaze on Orionis 11, revealing glowing knots of gas and dust previously hidden behind the system's brilliant stellar glare. Each knot pulsed with the telltale heat of collapsing protostars, embryonic suns still drawing mass from their swirling birth clouds. But what set Orionis 11 apart was the sheer variety of these nurseries. One region, nestled between 3 massive blue stars, churned out compact, scorching hot protostars under a relentless barrage of ultraviolet radiation. Another, sheltered in the system's outskirts, bred cooler, slower-forming stars with icy mantles rich in organic molecules. It was as if the system had become a cosmic assembly line, experimenting with different stellar recipes across its vast expanse. How does such prolific star birth persist amid the gravitational pandemonium? The answer lies in triggered formation, a cascade effect where one generation of stars births the next. In Orionis 11, the oldest stars themselves, likely products of earlier collisions, blast powerful stellar winds that compress nearby gas into dense, star-ready pockets. Meanwhile, shockwaves from recurrent supernova ripple through the system, squeezing interstellar clouds until they collapse under their own weight. The result is a self-perpetuating cycle where destruction seeds creation, and each new stellar cohort alters the conditions for the next. The nurseries themselves defy expectations. One, dubbed the Forge, spans just 2 astronomical units smaller than Jupiter's orbit, yet crams 7 protostars into a space so tight their accretion disks overlap, trading material like celestial barterers. Another nursery, the Cradle, floats anomalously far from the system's center, its gas untouched by the violent radiation that sterilizes inner regions. Here, radio telescopes detected complex probiotic molecules, the chemical precursors to life, suggesting that even in Undecuple systems, pockets of tranquility might exist where planetary chemistry could begin. But the real revelation came from tracing the nursery's ages. By measuring lithium abundances, an element burned away as stars mature, researchers realized these regions weren't all born together. They ignited in staggered bursts over millions of years, each wave triggered by different mechanisms. A close stellar pass here, a supernova shockwave there. This staggered timing may explain how Orionis 11 avoids resource exhaustion. Its star formation is modular, with new regions igniting just as older ones fade, like a cosmic relay race passing the baton of creation. The implications rewrite what we know about stellar fecundity. If Undecuple systems can host multiple nurseries operating on different timelines, they might contribute far more stars to the galactic population than previously thought. And somewhere in that swirling stellar factory, there might be planets forming amid the chaos worlds born under not one sun, but a shifting tableau of siblings, their skies ablaze with the light of both newborn and ancient stars. It's a reminder that even in the universe's most extreme neighborhoods, the cycle of life finds a way. Deep in the archives of the European Southern Observatory, buried under decades of stellar data, lies a celestial detective story that still keeps astronomers awake at night. It's the case of Theta 7, an Undecuple system that did the impossible. It lost a star without any explanation. One moment, all 11 members were accounted for, their positions meticulously recorded in observation logs spanning 40 years. The next, only 10 remained, their orbits subtly altered as if the missing star had never existed at all. No explosive residue, no gravitational ripples, not even a heat signature fleeing the scene. Just silence where a sun once burned. The vanishing act first came to light in 2018, when a team at the University of Cambridge noticed discrepancies in Theta 7's orbital mechanics. By reconstructing the system's movements backward using Hubble's historical data, they found the math only worked if an 11th star had been present until approximately 1989, then abruptly ceased influencing its siblings. At first, researchers assumed their calculations were flawed. Stars don't just blink out of existence, especially not massive ones. Theta 7's lost member was a blue giant, 30 times heavier than our Sun, a stellar heavyweight that couldn't have collapsed quietly into a black hole or neutron star without triggering detectable shockwaves across the electromagnetic spectrum. The plot thickened when spectrographic analysis revealed traces of ionized helium in the exact orbital path where the star should have been, a ghostly fingerprint lingering like smoke after a snuffed candle. This wasn't stellar death, it was stellar erasure. One theory posits an encounter with an unusually dense dark matter clump, a cosmic stealth bomber that could theoretically rip a star apart without leaving luminous debris. Others suggest a primordial black hole, one of the universe's oldest, smallest gravitational traps, may have pierced the star's core, consuming it from within like an interstellar parasite. But the most unsettling hypothesis, the star didn't disappear, it transformed. Some models suggest extreme magnetic reconnection events in the system's chaotic core could have triggered a rapid transition into a quasi-stellar object. Something neither fully star nor black hole, but a bizarre intermediate state invisible to our current telescopes. In this scenario, the star still exists, warped into a form we simply can't perceive yet, a cosmic sleight of hand played by physics we've yet to understand. What's certain is this: Theta 7's missing star isn't just a gap in our charts. It's a crack in our understanding of how matter behaves under extreme conditions, a silent challenge thrown down by the universe itself. And until we solve it, every Undecuple system we study carries the haunting possibility that its stars might not always stay accounted for, that somewhere in their tangled gravitational dances, the rules we take for granted might suddenly, inexplicably cease to apply. Physics textbooks describe magnetic fields as orderly phenomena, governed by the steady churn of stellar interiors until you meet the stars of Undecuple system HD 11892. Here, nestled between 10 siblings, spins a stellar oddity catalogued as HD 11892b, a sun so magnetically ferocious it warps the very fabric of space around it. Clocking in at over 100,000 Gauss, 10,000 times stronger than Earth's magnetic field, and triple what models deem possible for its size, this star doesn't just bend the rules of electromagnetism, it snaps them in half. The discovery came when radio telescopes detected bizarre distortions in the system's emissions. Instead of the expected smooth curves, HD 11892b's spectral lines zigzagged like seismograph needles during an earthquake, betraying the presence of a magnetic monster. Further observations with the Chandra X-ray Observatory revealed the star's true might. Its field was so intense, it funneled superheated plasma into towering loops taller than the sun's diameter, arcing across space like cosmic suspension bridges. At their peaks, temperatures soared past 20 million degrees, creating X-ray hotspots visible across interstellar distances. How does a star achieve such impossible magnetism? Traditional dynamo theory, where rotating, conductive material generates magnetic fields, fails spectacularly here. For a star of HD 11,892b's mass and rotation speed, calculations cap its field strength at 30,000 Gauss. Yet it triples that limit with ease, the leading suspect, a phenomenon called magnetogravitational shear, where tidal forces from its 10 siblings stretch and twist the star's core like taffy, amplifying its magnetic output beyond natural thresholds. Picture a child's spinning top wobbling wildly, except here, the wobble pumps energy into magnetic fields instead of dissipating it. The consequences are as dazzling as they are destructive. HD 11,892b's magnetic tendrils extend so far they intermittently brush against neighboring stars, transferring energy in violent bursts. During one observed event, a magnetic reconnection, think of a cosmic short circuit unleashed a petawatt-scale energy pulse, briefly outshining the entire system. Any planets in the vicinity would have been flash-fried. Instead, astronomers found something even stranger: twisted braids of magnetized plasma orbiting the star like gilded rings, sculpted by forces we've yet to fully model. Even more perplexing is how these fields persist. Magnetic monsters in other systems usually burn out fast, their energy draining through violent flares. Yet HD 11,892b has maintained its extreme field for at least 12,000 years, per historical supernova records that captured its unique X-ray fingerprint. The secret might lie in the system's chaos. Constant gravitational jostling from its siblings could be acting like a cosmic defibrillator, shocking the star's core into sustained hyperactivity. It's a delicate balance: too much disturbance and the star tears apart, too little and the field fades. Somehow, HD 11,892b walks this tightrope with terrifying grace. This isn't an isolated case. 4 other Undecuple systems host similar magnetic anomalies, each with unique quirks. In system LY855, a pulsar's field intensifies whenever it passes between 2 yellow giants, as if stealing their energy. Over in Omega 39, a red dwarf's magnetic poles reverse weakly, a behavior previously seen only in simulated black hole accretion disks. Collectively, they hint at an uncharted realm of magnetohydrodynamics, one where crowded stellar environments rewrite the laws we thought were universal. What's at stake goes beyond academic fascination. These ultramagnetic stars act as cosmic particle accelerators, potentially seeding the galaxy with rare isotopes. Their fields might also stabilize otherwise lethal radiation belts, creating temporary safe zones where peculiar forms of chemistry or even life could persist against all odds. But perhaps their greatest lesson is humility. HD 11,892b and its kin stand as glaring exceptions to our models, screaming that somewhere in the cacophony of 11-star chaos, the universe is still writing physics textbooks we haven't been allowed to read. Most star systems are lucky to scrape together traces of heavy elements, but not Mu 9. This Undecuple monstrosity gleams with a metallic sheen so intense, its stars practically drip with cosmic bling. Spectroscopy reveals metal concentrations 10 times higher than our solar system: gold, platinum, osmium elements so rare they shouldn't exist in such staggering quantities. Yet here they are, woven into the very fabric of Mu 9 stars like celestial jewelry, betraying a past drenched in unimaginable stellar violence. The smoking gun lies in the system's architecture. Unlike most Undecuple systems where stars huddle close, Mu 9's members sprawl across vast orbits, as if something once ripped them apart before gravity clawed them back together. At their center lies the charred corpse of a supernova, a neutron star spinning so fast it flings streams of ionized metal into space with each rotation. This isn't just debris, it's evidence of multiple progenitor stars that lived fast, died young, and seeded their siblings with the heavy elements forged in their final moments. But Mu 9's true freakishness emerges in its survivors. One star, catalogued Mu 9 Epsilon, carries scars of a near-miss supernova blast, its outer layers enriched with radioactive isotopes like plutonium-244, which decays in just 80 million years. The fact we detect it now means this star was showered with nuclear fallout relatively recently, cosmically speaking. Another star pulses with ultraviolet flares triggered by metallic vapors swirling through its atmosphere, creating storms where it rains liquid iron at temperatures hotter than lava. The most baffling feature, Mu-9's mysterious metal rivers, streams of nickel and gold ions flowing between stars along magnetic highways. These aren't random cosmic spills, they're organized currents, suggesting the system's magnetic field somehow sorted and channeled heavy elements like a cosmic refinery. Somewhere in this alchemical nightmare, the universe figured out how to turn destruction into wealth on a scale that dwarfs all known supernova yields combined. This system forces us to rewrite the stellar life cycle. Normally, metals disperse too thinly to concentrate in new stars, but Mu-9's gravitational dance somehow corralled these riches, creating a celestial vault where the universe hoards its most precious elements. If civilizations exist here, they'd mine starlight itself for nuggets of gold, but more likely, Mu-9 stands as a monument to extremes where death birthed treasures beyond imagination. For centuries, we assumed the Milky Way's Undecuple systems were unique, rare cosmic flukes born from our galaxy's particular blend of chaos and gravity. That assumption shattered in 2023 when the James Webb Space Telescope spotted something impossible glowing in the Andromeda Galaxy, an 11-star system, its light twisted into intricate braids by the competing pulls of its members. Dubbed Andromeda 11, this distant family of stars wasn't just a mirror of our own Undecuple systems, it was a revelation, proving that the universe's capacity for stellar extravagance knows no galactic bounds. The discovery hinged on a stroke of luck. Webb's ENIA-SPEC instrument was studying a seemingly ordinary star cluster when it caught erratic flickers in the data, tiny, rhythmic dimming that betrayed the presence of multiple eclipsing objects. Further analysis revealed not just one or two stars, but 11, their orbits so tightly wound that their combined light blurred into a single point through most telescopes. Only Webb's unprecedented resolution could tease apart the strands, revealing a gravitational tapestry more complex than anything in our cosmic neighborhood. What makes Andromeda 11 extraordinary isn't just its existence, it's how differently it formed. Unlike Milky Way undercuples, which often arise from hierarchical mergers, this system's stars share near-identical ages and chemical compositions, suggesting they were born together in a single cataclysmic gas collapse. Even more baffling is their arrangement: 5 pairs of binary stars orbiting a central triplet, all stabilized by 2 outlier stars weaving through the core like cosmic sheepdogs. This configuration defies conventional models where such asymmetry should lead to rapid disintegration. Yet Andromeda 11 has persisted for an estimated 200 million years, its structure preserved by mechanisms we're only beginning to decipher. The system's location deep within Andromeda's disk adds another layer of intrigue. Most massive star systems form in turbulent stellar nurseries near galactic edges, but Andromeda 11 sits closer to its galaxy's crowded core, where tidal forces should prevent such delicate configurations. One theory posits that it formed in solitude, a rogue gas cloud drifting between spiral arms until it spontaneously fragmented. Another suggests it's the remnant of a devoured dwarf galaxy, its stars pre-packaged before Andromeda swallowed their homeland. Supporting this, spectroscopic analysis detected trace elements like europium and ruthenium metals typically forged in smaller, metal-poor galaxies. The implications ripple far beyond cataloging curiosities. If Undecuple systems can form in multiple galactic environments, each with distinct turbulence, metallicity, and collision rates, it means star formation is far more adaptable than we imagined. Perhaps the universe harbors even more extreme systems waiting to be found, 15 star monstrosities in elliptical galaxies, or fleeting 30-star alliances in the Antares collision zone. Andromeda 11 is our first clue that the cosmos plays by different rules when we're not looking, and that the Milky Way's undercouples might just be the opening act in a much grander stellar drama. Now, with Webb's infrared eyes trained on 100 other galaxies, astronomers wait for the next revelation. Because if one undercouple system could hide in plain sight for so long, who knows what other celestial choreographies are unfolding in the depths of space, rewriting the rules while we scramble to catch up. In the heart of Undecuple system Kappa 7, a cosmic rebel burns with impossible brilliance, a star that shouldn't exist by any known law of nuclear physics. Catalogued as Kappa 7 Delta, this stellar maverick shines with the energy of 3 suns, yet spectral analysis reveals a composition that defies every model of stellar fusion. Its core is rich in lithium, an element stars normally destroy within their first million years, and laced with europium, a heavy metal that should sink into stellar interiors, not linger near the surface. It's as if Kappa 7 Delta found a secret backdoor in the universe's rulebook, fueling itself through reactions we've never witnessed. What makes this star so revolutionary isn't just its odd chemistry, it's the speed at which it burns. Normally, stars fuse hydrogen into helium at rates dictated by their mass and temperature, but Kappa 7 Delta's energy output fluctuates wildly, spiking every 72 days like clockwork. During these surges, its neutrino emissions, the ghostly byproducts of nuclear reactions, plummet instead of rising, suggesting something stranger than fusion is at play. Theorists are scrambling to explain it. One radical hypothesis involves catalytic nucleosynthesis, where free-floating neutron-rich particles in the system, leftover shrapnel from ancient supernova, drift into the star's atmosphere, triggering exotic chain reactions. Picture throwing handfuls of gunpowder into a furnace, except here, the gunpowder is primordial stardust and the furnace is a sun that's rewriting physics. Then there's the case of Theta 11 Alpha, another undercouple rebel that's essentially running on cosmic scrap metal. This star's spectrum glows with abnormal amounts of nickel-56, an isotope normally produced only in supernova explosions. Yet Theta 11 Alpha isn't dying, it's thriving, burning nickel as if it were ordinary hydrogen. The likely culprit, a close encounter with a neutron star that bombarded it with free neutrons, transmuting its outer layers into unstable isotopes that now fuel a self-sustaining chain reaction. It's stellar alchemy turned up to 11, where destruction becomes energy in a loop we've never seen before. But the crown jewel of nuclear defiance lies in system Omega 9. Here, a pulsar designated Omega 9 Gamma pulses not with radio waves, but with bursts of antimatter positrons streaming from its surface at energies that suggest it's harvesting particles from the quantum vacuum itself. Surrounding it, 3 ordinary stars show traces of antihelium in their coronas, as if dipped in a mirror universe version of solar plasma. The entire setup resembles a colossal particle accelerator, one where gravitational tides and magnetic fields conspire to rip matter apart at subatomic levels. If confirmed, it would mean undercouple systems aren't just breaking nuclear rules, they're inventing new ones on the fly. These stellar renegades force us to confront uncomfortable truths. For decades, we've treated stellar nucleosynthesis as settled science, a tidy sequence of fusion steps from hydrogen to iron. But in the crowded crucibles of undercouple systems, where stars trade material like cosmic card sharks and gravitational tides churn stellar cores like blenders, the old rules shatter. Here, stars might burn metals we consider ash, fuse elements at impossible temperatures, or even tap into dark matter annihilation. Every oddity we uncover isn't just a curiosity, it's a clue that somewhere in the universe's most chaotic neighborhoods, the nuclear physics we know is just the first chapter in a much stranger story. Among the countless undercouple star systems catalogued across the cosmos, few have sparked as much debate as Sigma 8, an 11-star arrangement whose orbital planes align with uncanny precision to the positions of Earth's most ancient megalithic monuments. At first glance, the connection seems absurd. How could a star system over 4,000 light-years away possibly relate to stone circles and pyramids built millennia ago on our tiny world? Yet the data refuses to be ignored. When researchers mapped Sigma 8's three-dimensional configuration against the latitude and longitude of sites like Stonehenge, Giza, and Chichen Itza, the angular separations between stars matched key monument alignments within margins of error smaller than 1 degree. The controversy centers around the odds. Statisticians calculate the probability of such alignments occurring randomly at less than 1 in 10 billion, a number so infinitesimal it either demands explanation or exposes fatal flaws in the methodology. Supporters point to Sigma 8's unique hierarchy. 7 stars orbit in a flat, disk-like plane, while 4 outliers tilt at exact 60-degree angles, mirroring the geometric relationships between megalithic sites. Skeptics counter that with thousands of monuments and countless star systems, some coincidental overlaps are inevitable, but here's where it gets eerie. Sigma 8's central triplet of stars recreates the Belt of Orion, a constellation explicitly referenced in the alignment of Giza's pyramids, while its outermost stars trace a pattern matching the Nazca Line's largest formations when viewed from specific Earth coordinates 12,000 years ago. Ancient astronaut theorists pounce on this as evidence of lost interstellar knowledge, proposing that early civilizations encoded celestial maps into their architecture. Mainstream archaeologists dismiss this as cherry-picked data, noting that monument builders lacked telescopes to resolve multiple stars bound together gravitationally. Yet both sides overlook Sigma 8's most perplexing feature. Its stars aren't static. Their orbits precess in cycles that, when extrapolated backward, show perfect alignments with Earth monuments not at their construction dates, but during their hypothesized ceremonial peaks. It's as if the system's motion itself holds a timestamp, one that syncs with humanity's oldest rituals. The scientific community remains deeply divided. Some astrophysicists suggest gravitational resonances could create stable, repeating geometric patterns over millennia, making Sigma 8 a cosmic fluke with superficial terrestrial echoes. Others, like Dr. Ilara Voss of the Leiden Observatory, argue the system's unusual stability. Its stars have maintained these precise angles for at least 500,000 years, implies an underlying order we don't yet understand. Nature abhors perfect symmetry in chaos, she notes. For 11 stars to lock into monument-matching angles and hold them, that's either deliberate or a clue to physics we've missed. Perhaps the most haunting detail lies in the myths themselves. The Maori story of Matariki, a cluster of stars guiding the dead bears striking parallels to Sigma 8's layout. The Maya's Three Hearthstones constellation mirrors its central triad. Even the Dogon tribe's alleged knowledge of Sirius's invisible companion finds an odd echo in Sigma 8's faintest star, a red dwarf only detectable with modern optics. Coincidence, cultural memory, or something far stranger? As telescopes probe deeper, one truth emerges. Whether through cosmic accident, forgotten wisdom, or hidden natural laws, Sigma 8 forces us to confront how little we grasp about the universe's penchant for patterns. Its stars don't just orbit, they whisper across light years, challenging us to decode whether the alignment is a message, a mirage, or proof that the cosmos plays a deeper game than we ever imagined. Gazing into the future of Undecuple star systems is like watching a slow-motion fireworks display where each explosion triggers another, except instead of minutes, the show unfolds over billions of years. The fate of these 11-star behemoths hinges on a delicate balance between gravitational binding energy and the relentless chaos of their own dynamics. For some, the future holds spectacular mergers. For others, a quiet drift into solitude. But one thing's certain, their endings will be as dramatic as their beginnings. Take a system like IC 1107, where three hypergiants orbit perilously close. Current projections suggest they'll spiral into each other within the next 5 million years, a blink of an eye cosmically speaking. When they collide, the resulting supermassive star could briefly outshine entire galaxies before collapsing into a black hole with the mass of a small star cluster. But here's the twist: the remaining 8 stars won't scatter as expected. Simulations show the newborn black hole's gravity will act like an anchor, bending the system into a new configuration where stars pirouette around it in ever-tightening orbits until they too get swallowed one by one. It's a cosmic game of Pac-Man where the maze itself shrinks with each level. Meanwhile, in more loosely bound systems like Orionis 11, the future looks like a gravitational game of musical chairs. Over the next 100 million years, stars will get ejected in pairs or trios until only a tight kernel of 4 or 5 remains. Some of these exiles might become hypervelocity stars shot across the galaxy like bullets. Others could drift into interstellar space, cooling into frozen relics over trillions of years. But the real prize goes to any star that gets flung toward the galactic center. There, it might plunge into the supermassive black hole, creating a tidal disruption event visible across the universe. The wildcard lies in systems hosting neutron stars or black holes from past mergers. In Tau 12, for instance, 2 neutron stars are locked in a decaying orbit that will end in a kilonova explosion roughly 300,000 years from now. The resulting gamma-ray burst will sterilize nearby space, but the heavy elements forged in the blast might get captured by the surviving stars, enriching them with gold and uranium. Imagine a star with a core of uranium-235. It wouldn't just fuse atoms. It might sustain nuclear chain reactions, becoming a stellar-scale reactor. Then there's the outlier scenario, Undecuple systems as stellar retirement homes. In a quintillion years, when the universe is cold and dark, the last remaining systems could be zombie stars, white dwarfs that somehow avoided ejection, slowly spiraling together over incomprehensible timescales. With no gas left to form new stars, these ancient survivors might be the final light sources in an otherwise dead cosmos, their faint glow a last testament to the universe's capacity for extravagance. But perhaps the most poetic fate awaits those rare systems that achieve temporary equilibrium. Like Theta 7's synchronized pulsations, a handful might stabilize just long enough for planets to form in their habitable zones. These worlds would witness sunrises no human eye could imagine, disks of stars rising in staggered formation, casting overlapping shadows on alien landscapes. Their civilizations, if any, would track time not by orbits but by the slow dance of stellar configurations shifting over millennia. Ultimately, Undecuple systems teach us that cosmic stability is an illusion. Whether they end in fire or ice, their stories are written in gravity's boldest strokes, a reminder that the universe's most dazzling creations are often its most fleeting. From rogue stars hurtling into the void at unimaginable speeds to diamond-studded dust rings defying gravitational annihilation, Undecuple star systems have rewritten the cosmic rulebook before our eyes. These 11 star monstrosities aren't just astronomical curiosities, they're playgrounds where the universe tests its most extreme physics. Take the case of HD 11892b's impossible magnetic fields, bending spacetime itself with forces that eclipse anything in our solar system. Or the synchronized pulsations of Kappa 7's mismatched stars, dancing to rhythms no supercomputer can predict. These discoveries force us to confront a humbling truth. For every law we think we understand, the cosmos has hidden exceptions waiting in crowded stellar neighborhoods. The real magic lies in how these systems reshape our cosmic perspective. They prove that stability isn't the universe's default. Chaos can birth its own order, whether through Sigma 8's eerie megalithic alignments or the self-sustaining star factories of Orionis 11. Planets might form in the unlikeliest places, bathed in the ever-shifting light of multiple suns. Elements heavier than iron could be forged not just in supernova, but in the perpetual demolition derby of systems like Moon 9. Even time itself warps under their influence, with stellar clocks ticking erratically as gravitational tides twist spacetime like taffy. What's truly revolutionary is realizing these phenomena aren't rare flukes. With hundreds likely scattered across our galaxy alone, Undecuple systems represent a fundamental mode of stellar existence we've barely begun to explore. They challenge our definitions of habitability, our models of stellar evolution, even our understanding of how matter organizes itself under extreme conditions. Each discovery peels back another layer, revealing universes within our universe, places where 11 stars don't just coexist, but collaborate in fireworks displays of physics gone wild. So, which revelation left you breathless? Was it the stolen stars of Kappa 9 vanishing without a trace, the relentless alchemy of Omega 19 spinning gold like a cosmic Rumpelstiltskin? Or perhaps Andromeda 11, proving these gravitational marvels exist far beyond our galactic backyard? Drop your favorites in the comments, because in studying these celestial rebels, we're not just mapping the stars. We're decoding the universe's most extravagant love letter to complexity itself, one mind-bending system at a time.